There are many variations for the Kalman filter, and we're not going to be talking about all of them, but one I think that's representative of some of the changes you might see is the extended Kalman filter. Kalman filters, as we've developed them, work for linear systems. We have x is equal to some matrix A times x plus noise, so the relationship between x at time n is linear relative to the relationship x at time n minus 1. So how do we deal with a system that might be nonlinear in its states? Well, there are different types of linearity or nonlinearity that we might deal with. For example, we may have a system where we can create a linear model from a nonlinear system. So one such system could be the standard acceleration position equation from physics. In this case, the position at time t is equal to the starting position plus the velocity times time plus 1/2 acceleration squared. And you could, of course, extend this to multiple dimensions. So this is nonlinear in time. How do we deal with that? Well, we can linearize it by approximating this in a linear fashion, as we did earlier in some of the examples. In this case, we took our position, velocity, and acceleration, discretized this, and then essentially we're numerically integrating by having the velocity increase by the acceleration and the position increase by the velocity. And so in so doing, we've now effectively rendered this nonlinear system as a linear system. So this is a valid approach. We've already seen it. It seems like a natural thing to do. What happens if we have some more tricky nonlinearities that don't lend themselves to such an approach? What if, for example, there was a transcendental function or a trigonometric function of the state? What could we do then? Well, actually, with some of those, we can enter into some linearized relationship, but for the moment, we'll assume that we can't. In these cases, we can approximate the system, the nonlinear system, as a linear system on the fly. To do this, assume first that we have some system where we have x of n is equal to some function of the previous state and the noise, and this function is nonlinear. We could also, of course, have our observation follow the same type of a situation, where y of n is equal to g times x of n v of n. So at time n, before we do our updates, our state update, we say that a is the derivative with respect, so it's multidimensional, perhaps I could have used a different notation, with respect to the current state estimate of f of x. Actually, let's write this slightly differently. Evaluated there at x of n minus 1. And we'll do the same thing, of course, for c. So we would have c of n is the derivative with respect to x of our g of x. It may also be a function of v, but we're only taking the derivative with respect to g. And in this case, we evaluate it at x of n, or I predict x of n. Okay, so a and c are now dependent on x of n and on time. So this is going to actually work quite well for well-behaved systems. So an example of how this might look would be if we had some f of x as a function of x like this. We're plotting here a one-dimensional system. Suppose that our operating point were this, then our a is going to be given by the tangential curve, which I'm not great at drawing. There we go. A little bit later, maybe we're down here, and we now have a new state update that looks like so. So this is a little bit of extra work, especially if f is a complicated function. But as long as it's known ahead of time, the Kalman filter with a small enough step size or high enough sample rate, if you will, it can be easily modified then to work for a nonlinear system.